Good evening. This is Professor Shannon Gracie back again. We are working out of the Precalculus Enhanced with Graphing Utilities text by Sullivan and Sullivan. And today we'll be going over section 2.2, which covers the graph of a function. So we'll be identifying the graph of a function and obtaining information from or about the graph of a function. So let's warm it up by graphing these equations just by plotting points. We'll be learning some different graphing techniques as we go along, but this is always something useful to use. So pause the movie, warm it up, and then see how you did. Okay, let's see how it went. I'm just going to do the regular scale on this, which is plus or minus 10 of x and y. So if we were to make a table of values for this, it's going to be easiest to plug in values for x and then solve for y. Whoa. And then here would be our ordered pair in terms of x and y. So if x is, let's try -3, y would be -3 squared, so y would be 9. So we'd have the ordered pair, -3, 9. Next up, plug it in -2. Y would be -2 squared, which would give us +4. So we'd have an ordered pair at -2, 4. And then at 0, y will be 0 squared. So y would be 0. So we've talked a bit about symmetry as we go along. Remember, there is a fold line at the middle of this graph. And we've also, I believe, talked about symmetry and the fact that this is going to reflect across the about the y-axis, because if you plug in -x for x, you get the same equation back out. So I'm going to use that information to get my last two ordered pairs. So here we go. X equal to -3 is on the graph, and we had an output at 9. So that means that when x is +3, we'll have an output of 9 as well due to symmetry about the y-axis. And then at x is -2, we had an output of 1, 2, 3, 4. Using symmetry at +2, we'll also have an output of 4. So our graph will look something like this. I'm not too crazy about that side of it. That's better. All right, how'd you do? Awesome, I knew you could do it. Okay, let's move right along. Now this one, what kind of graph is this? Y is raised to the 1 power, x is raised to the 1 power. You got it. It's a linear equation in two variables. So I'm going to use all of our skills that we know about lines to make the graph of this equation. So what will our slope be? So remember, y equal to mx plus b is the slope-intercept form of the line. So if I rewrote our line, we would have this. So my slope is, 3, which is the same as 3 over 1. And my y, actually the b, is -1. So I have an ordered pair at 0. -1 is my y-intercept. And then using the slope, I go 1, 2, 3 up and 1 to the right. You can also go 1, 2, 3 down and 1 to the left, because you can say m is +3 over +1, or m is -3 over -1. So I'm going to get a few more points. So I do a straight line. 1, 2, 3, and then 1. 1, 2, 3 down, 1 to the left. And there we go. We've got our line. Okay, you all warmed up now? Very good. So next up, we get to the vertical line test for functions. So if any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. So it's kind of weird because you're looking to see if it fails or not. So here, do you see there's infinitely many spots where we would intersect this graph in more than one point if we drew a vertical line, right? So this guy fails. So we need to answer the question, and the answer is no, this graph is not that of a function. What about part B? So here, you see it only passes in one spot. I mean, wherever we choose to draw a vertical line, it's only going to pass through one ordered pair. So this guy passes the test. So our answer would be yes. Good so far? Awesome. So next up, this one. Again, it looks like it's getting vertical. It's just getting very, very steep. So this one also passes. So our answer is yes. Okay. So now we're going to look at obtaining information from graphs. So you can obtain information about a function from its graph. At the right or left of a graph, you will often find closed dots, open dots, or arrows. A closed dot indicates that the graph does not extend beyond this point, and the point belongs to the graph, so it's part of the graph. An open dot indicates that the graph does not extend beyond this point, and the point does not belong to the graph. It goes just up to the point, but the point itself is not part of the graph. And then an arrow indicates that the graph extends indefinitely in the direction in which the arrow points. So if we were to kind of, draw a little picture of a graph just to get a feel for it and get a feel for domain and range. Let's say that we have, might as well get some. And this is x and this is f at x. So let's suppose we have something here, and let's suppose that this is, nope, sorry. This is at -8, 4, this open circle. And suppose that it swings down here and bounces and goes off like that. So let's determine the domain and the range of this graph. The domain is the left, all possible input values. So any input values that can go into whatever function you have. So if you just kind of look at the x values, do you see any walls there? So is there a left-hand side where you reach a wall where you have to stop, where the picture stops? Good. Yes, there is. You see here, there's a wall. So that means that at that x-coordinate, that is the end point for your domain. But will it be included? No, it will not. Good, because we have an open circle. So we get very, very, very close to x equals -8, but we never attain it. So if we wanted to talk about the domain here, the domain would be, if we did set builder notation, it would be x such that negative, actually, let's think about this. Is there a right-hand wall? No, good, because we have the arrow that goes indefinitely to the right. So there's just a left-hand wall. So that means that x is to the right of -8, meaning that x is greater than -8. So this is called set builder notation. More commonly used, or very commonly used, you'll see interval notation. Interval notation would have your end point, which is -8. It would have a parenthesis around it because it's not included, and it would go on to infinity. So this is interval notation. Okay. What about the range? So for the range, we're thinking floor and ceiling. So is there a floor on this graph? Is there a definite floor to here? Yes, do you see at 0, we've got a floor, right? But 0 happens to also be a point on the graph, right? An input value on the graph. So for our, for our range, we're thinking of the possible output values, right? So it would be in set notation y such that y is good, greater than or equal to 0. Because do you see that there is no ceiling because we keep going up, but there is definitely a floor. There's no y values below y equal to 0. So that's in set builder notation, and in interval notation for y, we would go from 0 to infinity. There's always parentheses around plus or minus infinity, but we would put a square bracket here. The square bracket means that 0 is part of the graph. So this y value here, we have an ordered pair at -1, 0, and that y value 0 is part of the graph. Okay. So let's review interval notation and set notation. So these are just these are number lines about x. So this would be, you know, specific information about domain. So here, if you have an open interval from a to b, let's just put our a's and b's on here. Should have just done this for you. Okay, so if you have an open interval from A to B, the graph looks like this. You do the parentheses, those are the equivalent of an open circle, and then you shade in between. Right? So in set builder notation, I'm getting a little crazy here. We would say x such that A is less than x, which is less than B. So that means the endpoints are not included. Now the next case are where the endpoints are included. So the graph, you use the square brackets. They're like the closed circle. And this would be x such that a is good, less than or equal to x, which is less than or equal to b. Now you could have one side included, one endpoint included, and one not. So here, if A is included, we'd have the square bracket around A, and if B is not included, we'd have the parenthesis, and we'd shade everything in between. So we would have x such that A is good, less than or equal to x, and x is less than B. Now, if B is the endpoint that's included and A, is not, the graph would look like this. So we would have x such that A is less than x and x is less than or equal to B. Okay, now you might just have one finite endpoint and the other is an infinite, right? Infinite. So positive infinity always is the rightmost. If you had a negative infinity, it has to be the leftmost. On the x-axis, positive infinity means infinite movement to the right, and negative infinity would mean infinite movement to the left. All right? So let's take a look at this. So if A is not included, you would just shade, and you would shade in the arrow as well. So this would be saying that x such that x is greater than A, because it's to the right of A. Now you could include the left endpoint, right? So then you'll have a greater than or equal situation. You could have just a right finite endpoint, not included. So if we're going from negative infinity to B, we would have x such that x is less than B. And if B is included, it's going to look like this. So we would have x such that x is less than or equal to B. And then you could have the whole real line. So this would be x such that x is an element of the real numbers. So this means is an element of or belongs to. And this one means real numbers. And if that was the case, that would mean that any value for x would work, and you would shade the whole number line. Okay, so here we are. Let's take a look at this graph, and we're going to use this graph to determine each of the following values. So basically, we have the scale is plus or minus 5 in either direction. So first of all, we're supposed to find f at 0. So if I plug in 0 for x, do you see I'm about here? It looks like the ordered pair 0, 2. So that means that we get an output of 2 when we plug in 0 for x. What about f at negative 2? Let's see where we're at. So if x is negative 2 and we go up, boop, 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 it looks like we're here at negative 2, 4. So what would my answer be? Good, 4. All right, let's turn it around a little bit. Now we're being asked to find what values of x, for what value or values of x is the function value equal to 3. So now we would go to y equals 3 and try to find the x value that would correspond. So here, if you look and kind of go across like this, you hit the graph here, and do you see that it's at about maybe negative 1.5? So negative 1.5, comma 3. So my answer to this one is when x is approximately negative 1.5. All right, now let's look at the domain of f is our next task. So, is there any wall on the left? Any stopping point on if you're looking left to right? I don't see a wall on the left because it keeps going and going, right, to the left, the x values. What about on the right? There looks to be a floor, but I don't see a wall on the right side. So that means, hey, it must be all good, all real numbers. So we're going to do this in interval notation. The domain is all real numbers, which is minus infinity to infinity. Now what about the range of x? Do you see a floor? I do. You see here? You hit right here a floor. But I don't see a ceiling because it keeps going up. So the floor looks to be when y is negative 4. So the y values that correspond to our range are going to be from negative 4 inclusive to infinity. So just in case you're better with Set Builder, in Set Builder this first one would be x such that x belongs to the real numbers, x is a real number, and then this one would be y such that y is greater than or equal to negative 4. Okay, doing okay so far? Awesome. So graph the following functions by plotting points and identify the domain and range. So go ahead and pause the movie. I feel confident that you can do these and go from there. All right, let's see how you did. So this one, the axes will be x and f at x. I think a standard scale will work just fine. And here, if you want, we could just find the intercepts. So the y-intercept will be when x is 0. So we'd be plugging in 0 for x. So f at 0 will be, good, negative 2. So we have an ordered pair at 0, negative 2. This is our y-intercept. Now, if you set the function value equal to 0 and solve for x, you'll find your x-intercept. So if I add x to both sides, I'll get positive x is negative 2. So my x-intercept will be this guy here. So at negative 2, 0, I get my x-intercept. And I'll just make the picture of the line. Okay, so this one is going to be a parabola. So if this is x and this is h at x, again, I think we can do our regular scale here. And we'll go ahead and find some function values. And we're also going to use symmetry. So here, do you see that this is going to be symmetric about the good y-axis? Because if I plug in negative x for x, I'll get the same thing back, the same function back. So that means that if I do h at 3, I'll get 3 squared plus 1, which is 10. So I have an ordered pair at 310, which means I'll have an ordered pair at negative 310 using symmetry. H at 2 is going to be 2 squared plus 1, which is 5. So at positive 2, 1, 2, 3, 4, 5, I have an ordered pair, which means at negative 2, 5, I'll have an ordered pair as well. And H at 0 will be 0 squared plus 1, which is 1. So I have an ordered pair at 0, 1. And we've got the shape of our parabola. Whoops. How'd we do? Doing okay? Great. Okay, so here we go. Let's take a look at this graph. So here's some interesting little questions. And we'll do the graph at the end on the graphing calculator to check it out. But first, is the point 1 3/5 on the graph? Well, if you plug in 1 for the x's and 3/5 for the function value, you can check it out. So we could say 3/5 is our function value. Is that equal to 1 squared plus 2 over 1 plus 5? So in for the x's I put 1, and in for f at x I put 3/5. So 3/5. Well, 1 squared is 1, 1 plus 2 is 3, and then, oops, I miswrote that here. 1 plus 4 was the original, so 3/5. So do you see that checks out? So we would say yes. 1 3/5 is a point on the graph because we got a true statement. Okay. If x equals 0, what is f at x? What point is on the graph of f? So if we plug in 0 for x, right? Remember it was x squared plus 2 over x plus 4. So f at 0 will be 2/4. So that would give us f at 0 is 1/2. So what does that mean? That means the point 0, 1/2 is on the graph of f. Okay so far? Great. Now, if the function value is 1/2, what is x? So it's asking us to solve for x here. So 1/2 is x squared plus 2 over x plus 4. So we want to multiply both sides by x plus 4 times 2 to clear both denominators. So on this side, the 2 divides out, and on the right side, the x plus 4 divides out. So we'll have x plus 4 equals 2x squared plus 4. Getting 0 on one side, we'd be subtracting x and subtracting 4 from both sides. So we would have 0 is 2x squared minus x, and then 4 minus 4 is 0. Factoring, we have x times 2x minus 1. So 0 is x, or 0 is 2x minus 1. Adding 1 to both sides, I'd get 1 is 2x. Dividing by 2, I'd get 1/2 is x. And we already knew that, didn't we? We knew that the point, we knew that, well actually, we knew that the point 0, 1/2 was on the graph of f, right? But now we know, what do we know? What points are on the graph of f? Well, the first x equals 0 gave us 0, 1/2, which we knew from the other problem. And we also got from solving this equation. So remember, we had plugged in a y value or a function value of 1/2. So both of these will have y values of 1/2. So 0, 1/2 and 1/2, 1/2 are points on the graph of f. Okay, so what is the domain of f? So let's look back here, the original graph. So remember, you start by thinking all real numbers, but this is a rational function, so what do we have to exclude? Good, any x values which will zero out the denominator. So x plus 4 cannot equal 0 because that was our denominator. That would give us that x cannot equal to -4. So the domain, so in set builder you would have x such that x is not equal to -4. And in interval notation we would have minus infinity to -4, non-inclusive. And then the way you join two intervals together is with this union symbol. And then we would go from -4 to infinity. So by doing the parentheses around each of those -4s, we basically said, hey, every input value except for -4. So this is interval notation. Okay, list the x-intercepts, if any, on the graph of f. Well, in order for us to have an x-intercept, we would have to have a real solution to the zeros of the graph. So this was our original. Make sure I didn't copy it wrong. There we go. So here, if you get a 0 in the numerator, that will zero out the fraction. So x squared plus 2 equal to 0. X squared would be -2, but you see that would be an imaginary numbers for your solutions. So we would say there's no x-intercepts. Okay, list the y-intercepts, if any. Well, the y-intercepts occur when x is 0, and didn't we already solve that? See up here, if x is 0, what is f at x? So we solved that in part B. So the y-intercept occurred at 0, 1/2. So actually, remember, in the Math Excel, it would just say y equals 1/2, or the My Math Lab. Good so far? All right, let's take a look at what this guy looks like on the graphing calculator, just for fun. So we would have y equals, let me clear this stuff out. So we had x squared plus 2, that quantity divided by quantity, x plus 4. So notice there's no x-intercept. Do you see that? No x-intercept. So this is, and that's where our x-intercept is. So let's see. Let's zoom out to make sure we have a full picture of the graph. Yeah, I thought we were missing half of it, right? So it's going to look something like this. I think we're not getting it all because of maybe our resolution. Let me change the resolution and see if that does anything. Ooh. You know, I don't like that here. That made it worse, didn't it? Okay. Well, I'll just keep it at 1. Get our picture. It's gives us an idea of what it looks like here. So let's put that up here. And all of the stuff that we found below, you can verify using the graph that you got on the graphing calculator. Okay, so now we're on to this application here. So if an object weighs m pounds at sea level, then its weight W in pounds at a height of h miles above sea level is given approximately by W at h is m times quantity 4,000 divided by quantity 4,000 plus h, all squared. So if Amy weighs 120 pounds at sea level, how much will she weigh on Pikes Peak, which is 14,110 feet above sea level? So let's see what we have here. What is M? Good, M is 120 pounds, right? What about H? Be careful, right? Do you see it's H miles? And do you see we have 14,110 feet? So we're going to have to change that. So we have to do a conversion here. So we have 14,110 feet, and we need to multiply that by 1. And the 1 we're going to use is for every 1 mile there are. Good, 5,280 feet. So do you see the feet will divide out? And let's take a look on the calculator and see what we get. So we would have approximately, we'll go to 4 digits, 2.6723. So H is approximately 2.6723 miles. So now let's plug everything in. So W at 2.6723 is approximately 120 times 4,000 divided by 4,000 plus 2.6723. Oops. That whole thing squared. So let's see what we get on our calculator. So 120 times parentheses 4,000 divided by quantity 4,000 plus 2.6723. This one ends the denominator parentheses. This ends the whole quotient, and then we're going to square that. and we get approximately 119.84 pounds. So let me paste that screen for you. Oops. Alrighty, now using a graphing calculator, let's graph this function. Now we have things in terms of, y and x. So our input value, our independent variable is going to be the x, and our dependent variable will be the y. So let's graph this. So we would have 1,400. Oh, wait, I was doing the wrong thing. Sorry, my bad. Let's see, it was 120 times 4,000 divided by quantity 4,000 plus x, because x is going to be our h, right? And then end that parenthesis, end the quotient, and square it, and then hit graph. So we held the 120 pounds constant, and so this is the picture we're going to get for this. So let's try a zoom fit. Let's see what we get here. Interesting. You know, let's do our own scale just to see. We don't need, for our x value, do you see we can start at 0? Right? Because the x value is the height. So 0 would be ground level or sea level. And then the x maximum, we were looking at, why don't we do, let's see, height above sea level. So do we really need to go that far above sea level? Why don't we go to 10 and see what it looks like? And then, so the weight will have a larger output. Why don't we just do, let's just do 0. And then for the y max, why don't we do 250? Right? Although it should be somewhere around 120, right? Because that's what the person's weight is at sea level. So you know what? We'll just do 120, 130, I think will be good. And then the y scale, we could do by 10 or 5. We'll just do by 10. Let's see what this graph looks like. Not very illuminating, is it? Okay. So at this point in time, it's good to kind of look at our y equals, well, maybe it does turn out, I was looking for it to be more curved because of this x value, but I guess it makes sense for it to be somewhat level. Let's just check our values, right? We had gotten a result of 119.84 pounds at h equals 2.673. So let's go ahead and do second calculate value, and let's enter in the 2.6723 and see if we get what we had gotten. Hey, you know what? That looks right. So let's go back to our graph, and one last time I'm going to mess with the window. We don't need the y min to be so low. So we'll go 100 to 130. And then the scale on y can just be 3. I'll do 3. Might be a nicer looking graph. Okay. Okay. Okay, so now we're being asked to create a table. So this one, remember, this here is that we did it from 100 to 130, and the x values went from, I think, didn't we do 0 to 5, I believe? Let's check it out. Our window again. Nope, we did 0 to 10. So 0 to 10 for our x values. So, and this was h, and this is w at h. Now they want us to create a table starting at 0 and the change in table to be 0.5 to see as h changes from 0 to 5 miles. So let's see what happens. So second table set. So they want us to start it at 0 to 0.5. And then we'll go. So what do we see happening? At sea level, same weight. And then as we keep going on, right, so we're going towards 5 miles, what do you see happening? It's decreasing, isn't it, slightly? You keep going, it'll decrease even more. So copy this one. So at what height will Amy weigh 119.95 pounds? So this one, it looks like at about maybe around 1 mile. That might be from rounding. So when h is approximately 1 mile. Does your answer to part D seem reasonable? Yeah, because at 2 miles it's decreasing, and at a little over 2.5 miles she was at 119.84 pounds. So yes. All right. So there we go. We're done with 2.2. Have a fabulous day, and I shall be speaking with you soon. Bye.